Good morning, class, and welcome to day one of Mr. Savaslow's paternity leave. If you recall, I did tell you that I'll be gone for a month, and in the meantime, you'll be doing lectures this way. Short video lectures, so you can pause, rewind, watch any little bit again. That makes the lectures go a lot faster, because I don't have to stop for you guys to catch up with your writing, because you can just pause whenever you need more time. So please take advantage of that, and please take advantage of the fact that you can re-watch this as many times as you need. All right, that said, let's go ahead and get started. Today we're talking about kinematics and graph matching. In other words, figuring out what motion graphs go with what other motion graphs. The big things we're going to talk about today are on the screen, the equations and how we can solve them. You guys know the algebra, but it doesn't hurt to go over it very quickly. What these three equations look like when graphed, why we care about them. And then we get to the graphing matching part. So figuring out what graphs go with what, and reasoning our way through that using not just the equations and plotting points, but also our logic and our understanding of how numbers work. And then we'll wrap up with a quick conversation of average versus instantaneous, as you can tell from a graph, and that will conclude our video lecture for today. So the three big equations, which I've already given you, are on the screen in front of you. The big idea here is these are the things that can tell you something's acceleration, position, velocity, and time at any point in time or space, as long as you know some stuff about how it began. The first equation requires that you know what speed it started at, what velocity it started at. The second one requires that you know its position and velocity that it started at. The last one as well requires both knowledge of the position and speed at the beginning. And remember, the beginning doesn't actually have to be the beginning. It can be any random point that you decide. Just like the final position and the final velocity doesn't really have to be the end. It can just be any point that you're interested in. All right, so let's jump into it. How to solve? All right, Vx equals V naught x plus AT. So first off, what do these things mean? Vx, that's our final velocity at some point of interest. The x just reminds us that we're talking about velocity in the x direction as opposed to the y direction, which we'll get to probably tomorrow. All right, V naught x, the zero, the naught, means initial, starting, at time equals 0. So that just says the initial velocity, plus the acceleration times the time. All right, so let's see. How would I use this? Well, if I'm solving for Vx, that's easy. I just plug my numbers in. A times t gives me an answer. Add it to V naught x, done. If I'm solving for V naught x, one step harder. Plug in my numbers for Vx, subtract my acceleration times time product, and I get my answer. And then finally, what if I'm solving for acceleration or time? Well, I got Vx, I got V naught x, I subtract to get the change in velocity, and then I just divide the other number that I have to get the number that I do not have. This one's a little more complicated. I don't think you are ever going to be asked to calculate the initial position, nor do I think you're going to be asked to calculate the final position. So the first thing that I would do, at least mentally, is I would get rid of that x naught, subtract it from both sides of the equation, so you have x minus x naught equals v naught xt plus 1/2 at squared. Because x minus x naught is our displacement. What we really care about almost all the time is not the final position or the initial position. It's how far did you go? What was your displacement? That will almost always be more useful to us than the actual solid position, as I will explain later when we get to the graphs. All right, so once you do that, if you're solving for delta x, easy, plug and chug. If you're solving for v naught, all right, well, you get your displacement, you get your 1/2 times a times t squared, where the squared just goes to that time. Then you subtract 1/2 at squared from both sides of the equation, divide both sides by t, and you're done. Now, if you're solving for acceleration using this equation, same basic idea. I have displacement, I subtract v naught xt, then I have to multiply by 2, and divide by time squared. Here's where things get tricky though. When you're solving for t, you'll need the quadratic formula, where you subtract x naught over to make delta x, or maybe more accurately, I should say, subtract x from both sides. And what you end up with is 1/2 at squared, a, plus v naught xt, b, minus displacement, c. And then you use your quadratic formula using a, b, and c, and all that crazy mumbo-jumbo to solve for the two possible answers of time. And then you have to use your logic to figure out which one's the real answer and which one is bogus. Good rule of thumb, if your time is negative, it's wrong. A negative time means that we're going backwards in time. We don't know how to do that yet. So it's a good chance that that's the wrong answer. All right, no, but there's a ray of hope. If your initial velocity is 0, then that entire term cancels out, goes away. And that gives you a much easier equation to solve for time with. And you don't need to use a quadratic formula. All right, this one, it already has x minus x naught in it. That's just displacement. Same deal, if I'm solving for Vx, I plug and chug, then square root at the end. Which, remember, a square root does not give me a positive answer. A square root gives me a positive answer and a negative answer. And again, you're going to have to use your logic to figure out which one of those two answers is correct. Sometimes they will both be correct. All right, same deal if you're solving for v naught x. You subtract 2a delta x from both sides of the equation, square root, it gives you a positive and a negative answer. You must have both answers and then logic your way to the correct answer from there. If I'm solving for acceleration, all right, I get my v naught x squared on the other side of the equation by subtraction, divide both sides by displacement, divide both sides by 2, and I got my answer. And by using the same process, I can get displacement. All right, it is my hope that that was boring to you. That is my hope. I put it in here just in case one or two of those things did trip you up or will trip you up when you hit your example problems. So you have some place to go back to, watch it again, and get some more hints on how to do it. All right, so what do these things look like when they're graphed? The first one, that is a linear function. It fits the y equals mx plus b format, where y is going to be vx, m is going to be acceleration, your slope, t is our x, is our independent variable, and then our b, our intercept, is going to be v naught x. And you'll see here in the upper left-hand corner that my initial velocity, my intercept, is -5. And my acceleration is +1, which means that for every second, the velocity gets +1. So, 1 second, -5 to -4. 1 second, -4 to -3. 1 second, -2. 1 second, -1. 1 second, 0. 1 second, 1, then 2, then 3, then 4, then 5. It does not matter that the initial velocity was negative. The velocity will change by +1 each second if the acceleration is +1. And that same thing is true regardless of where I start. Here I start at 5, 1 second 6, 1 second 7, 1 second 8, 1 second 9, 1 second 10. Now, if my acceleration is negative, the exact same thing happens, except instead of going +1, I'm going to do -1. Here I am at -3. 1 second, I'm at -4. 1 second, -5. 1 second, -6. Each second that passes, I do -1 to the velocity. Same deal over here. I start at 5. 1 second, -1 gives me 4. 1 second, -1 gives me 3, +3, and so on. And notice that the shapes of the graphs are identical. A positive acceleration will look like this on a velocity time graph, no matter what, and a negative acceleration will look like this, no matter what.